even agricultural green infrastructure. We're thinking about how to restore the ability of the surfaces of the earth to be able to absorb that water again and essentially enable it to function as a resource and not a waste product. Of course, there's always free water moving into the system every day through condensation. And as the water starts to migrate either up or laterally through our soils and in our geological zones, what we saw was recharge occurring across the whole of the cross-section of our geography, and our wetland and aquatic systems were essentially formed and sustained by constant, steady, stable discharge water, which maintained very stable hydrology, stable water temperatures, because the discharge zones were always around 52 to 54 degrees, and stable water chemistry year-round. We did not see a big fluctuation every time we got a rainfall in our aquatic systems. In fact, about the only time of year when we had anything running across the surface and depositing in our low-lying places like wetlands would have been in spring snowmelt. Pretty much the rest of the year, and we've got plenty of documentation, research, and other research that's been done that has proven the effectiveness of our historical ecosystems in terms of absorbing water, including a 100-year storm times 10 over the course of a 24-hour period. It was just amazing. And so very stable conditions. Now, the thing that's important about this is that virtually all of the terrestrial organisms and aquatic organisms throughout the face of North America and planet Earth, for that matter, are adapted to this kind of chemistry, this kind of water temperature, this kind of groundwater temperature, this living rhizosphere. I'll talk a little bit more about that later. What we've done across the face of urban, suburban, and rural agricultural North America is shift that historic groundwater-driven, stable hydrology 180 degrees on its face, so that now everything flows across the surface, and we build single-purpose infrastructure for the express purpose of dumping it and getting rid of it. So collection, conveyance, and discharge. That is the paradigm of modern engineering, which, of course, is not a very good idea when it's all said and done, because now what we do is we collect and convey virtually everything away from the site, overwhelming someplace else with it on a routine basis and leaving us starved of our own water. So our groundwater systems go down, and then we continue to suck more and more water out of the ground, and then it just keeps going down and down. And there's just a whole domino effect of disaster that occurs with that. So here we are everywhere USA Today, our street tree ordinances. You know, you have little uniform street trees every 25 feet, acres upon acres of drug-dependent rug, since most of North America's lawn systems aren't native to North America, like Kentucky bluegrass, which needs a lot of additional resources, including our own potable fresh drinking water, to keep it all robust and green, you see. And depending on where you live in the USA Today, that's somewhere between 35 and up to about 70% of the annual potable fresh drinking water consumption goes just to watering lawns. Now that's kind of absurd, but of course then what happens to all the water is it goes down the curb and gutter and it ends up going someplace else. We even design our landscape systems to send the water someplace else. Because the thing about the rug here, is it doesn't absorb water very well, so we need a little mini hole in the ground with a pipe to take the water over into the big hole in the ground. And then, of course, it takes all the undissolved constituents of the fertilizers, and the herbicides, and the pesticides with it. And heaven forbid that any of this water might leak back into the ground, because then we wouldn't be good engineers. It has to be a very enclosed storm sewer system to get rid of all the waste. And then after it's all dried out, it starts to turn kind of yellowish, so we now mine our potable fresh drinking water to keep it nice and green. And of course, we mass grade it out here because we don't want bumps and wet places in the wrong spots, and we have to take all that extra soil and create bumps. And then we put our plant material on top of the bumps in a highly compacted clay hole, and this is all now nice and compacted down too. And then we wonder why those plants die. When you think about plants growing in habitats to which they're adapted, I don't know of any plant that has any genetic history of growing on top of a highly compacted clay bump. So now we take all of our water and we sprinkle it back on here, wishing we had it back. And then what happens is this grows, which of course annoys us, because we can't have the truth looking until it's growing. So we mow it. And we mow it, and we mow it, and we mow it, and this life cycle of perpetual maintenance and cost associated with it, and spewing out 16 pounds of carbon dioxide, carbon monoxide, and other carbon corruption for every gallon of gasoline that we spew, and that's, of course, fossil carbon from 250 million years ago in the Paleozoic era. And, of course, then what happens to the water? Well, we take 15% of our property on average, 10% on the lease side, and we create holes in the ground. We have the dry bottom holes in the ground. We have the wet bottom holes in the ground. As landscape architects call these water features. And they're very unstable because all of the water goes into them very fast, and, the whole system. And then it goes out the other end. Often we put fences around it. I call this the water in jail syndrome. What you see, it's a waste product. It's not a resource anymore. And it goes out kind of like, as Jerry Wilhelm, my partner, says, like a lethal injection into our receiving waters, carrying all the crap with it. And along the way, it pollutes both our surface and groundwater with a whole bunch of things other than the nitrogen and phosphorus. But by the way, if you work for a community and you're now trying to deal with new emerging US EPA standards for nutrient reduction from your wastewater treatment facilities, you got a big problem. Because there isn't any waste treatment facility that I know that can meet with conventional standard or with conventional wastewater treatment technologies this kind of reduction. We can't. I'll talk more about that later. So what we've done is we've now reversed that entire historical process 180 degrees on its face. When water goes away, it goes away with energy, and it takes resources with it. We blame it on the rain, as if it's the rain's fault. And along the way, it rips up our built infrastructure, our historical natural infrastructure, and we see more and more and more examples of this at a frequency and a ferocity which would have been historically impossible. And if you look at statistics, we are seeing magnitude rainfall events that should occur have a percent of occurring about once every 100 years. We're seeing those events occur in frequencies in larger, surpassing 100-year rainfall events almost yearly, year after year. It's just, so there's something going on here. And I will tell you, we are causing it. And now here's what we're facing. You've got to have a sense of humor when you're dealing with this. And of course, we live in the hydrology boom and bust. When it rains, all water goes out of the system. When it doesn't rain, we're left in deficit. We're simply drying up. Now, I don't know too many aquatic organisms that can live in this for very long. It would have never been like that. So, and of course, the mathematical problem, you can't keep sending it away and think you're not going to run out of fresh water. And of course, plants have no genetic history of growing in these kinds of situations. And so here's what we have today. I call it the riparian schmutz, because we have no plants that have any genetic history of growing in a constantly inundated, filthy, water polluted habitat, except for a few Eurasian and native weeds. And so we lose our biodiversity, we lose our system stability, we lose a lot of money. So now there are emerging policies that support green infrastructure. Hey, maybe this is a good idea. Maybe we shouldn't send all of our water away. What can we do to help support keeping it? Well, I'm sure everybody's now familiar with a lot of the basic green infrastructure systems, green roofs and porous pavements and bioretention, rainwater harvesting, reuse, ancient technologies, wastewater recycling and reuse, that's cool stuff. Landscape systems, everybody talked a little bit about this yesterday. So whether you're designing a full-blown rooftop garden that has a lot of social and other benefits on top of energy and water, or whether it's an extensive green roof system, huge benefits, bundled benefits of vegetated green roofs. So it relates to water, relates to energy. Porous pavement systems, whether it's modular interlocking porous pavements, whether it's porous asphalts and concretes, they all have their place. Integrated bioretention, rainwater harvesting at the home scale and a more industrial scale. It's a 35,000 gallon that is a cistern that's been placed at Johnson Controls headquarters just north of Milwaukee. Biological waste treatment, wonderful opportunities for essentially eliminating the concept of waste. So rainwater and waste now become essential resources built right into your community, and of course integrated native landscape systems. You have about 1,000 native plants that are native to your community, and you have the ability to utilize them in systems of living communities. Cost savings, water savings, water infiltration, and the list goes on and on. A couple of examples of how communities have now begun to tackle the challenge of, is it cost effective to do this? So we started working in about 2009 in Charles City, Iowa, after the 2008 flood that devastated the community. This is what it looked like downtown. As you got up out of the downtown along the river corridor, you started to see that they had a lot of crumbling street infrastructure. In some cases, they had curb and gutter that was crumbling and falling apart. Had a lot of problems with ponded water in other neighborhoods. They had no curb and gutter at all. The storm sewer systems were old, grossly undersized. They had a lot of winter problems with freezing and thawing and freezing. And their sanitary sewer systems were now collapsing and falling apart as well. So they were getting intrusion, and people were getting sewer backups in their basements and nasty stuff. So this is kind of what it looked like in the beforehand. So we started working with them. It was a very hands-on community sort of effort, and slowly but surely looked at modular porous pavement streets with integrated bioretention into the parkways, and began implementing, now and counting, 28 linear blocks of completely retrofitted interlocking porous pavement streets and bioretention systems. And this is what it looked like going in, going down, just as we were wrapping it up. Now they're expanding this program every single year. Little Carbon Cliff, Illinois, just out by the Quad Cities. Population about 2,500. Worse infrastructure than what Charles City had. We came up with a plan, designed the retrofit for every street, give them new infrastructure, new sanitary. Obviously, the storm sewers aren't the same because we don't have conventional storm sewer systems in these streets. We don't want something that just conveys water away elsewhere. So we've now retrofitted them. They want a nice, clean curb and gutter. And this is basically what it looks like. We're retrofitting systematically every single street in the community. Now, what does this mean from a water management standpoint? Obviously, the infrastructure will last for generations. We're looking at 50-year cycles for infrastructure, and that's a conservative estimate. But from a water management standpoint, what does it mean to us? Well, using very, very conservative estimates, because when we designed both Carbon Cliff and Charles City, we were looking at being able to not only absorb the rainfall that's falling within the parkway, and in most of our communities, like I talked about yesterday, 50% or more of our communities are made up of our parkway systems, our streets and our parkways. So when a community, like my own community I live in Elmhurst, Illinois, is looking at a major multi-gazillion dollar storm sewer retrofit using every one of our parks for detention basins and big massive storm sewer interceptors, which drives me crazy because they don't have enough room to handle the problem. And I said, you don't have to pay a penny for a piece of private or public park infrastructure to buy land, and then so you can dump dirty polluted water in it, and then expect us to go out and play soccer in it a couple of days later. I'm sorry. You have all the public space that you already own, and that's right within your streets and the parkways of your street corridors. That's all you need to solve this problem, especially when other surrounding homes and businesses and schools and so on and so forth start to get on board and do something. So the way we designed these, looking very, very conservatively, just to give you some numbers. The average linear block length was about 350 feet, 24 feet from curb to curb, 2-foot base course with 36% pore space. Every linear foot of just had estimated storage of about 17 cubic feet or 6,000 cubic feet per block. Now that's just looking at 350 feet within that cross section, not incorporating any infiltration, not even incorporating the parkway bioretention. So basically what we did, just to give you an example, if we took 1 square block, half of the street cross section that wrapped around that block, because we know, using our most conservative estimates that we'll design, we can completely absorb a 2-year, 24-hour rainfall event within the street cross section, taking complete runoff from the alleys and from the homes, as if they're doing nothing within their sites. So let's just use, and this varies a lot. Let's just use this for purposes. So let's say you have a 2.5-inch rainfall, which is somewhere around between a 1 to 2 year storm event. You take about 3.2 acres of land, and we're cutting about 28,000 cubic feet of runoff completely absorbed within that cross section, just within the streets, or about 210,000 gallons per block reduction for a 2 year, let's say 1 to 2 year rainfall event. Now, if you're a community like your community here in South Bend that has a combined storm sanitary sewer system, you can start to see what that could mean to you in terms of cost reductions, sending stormwater now into your municipal wastewater treatment facility and having to treat that in larger rainfall events. We're talking about 90% of our rainfall events never leaving the block. And even when we get our larger rainfall events, let's say you get a 50 or 100 year rainfall event, these are using the most conservative numbers. We honestly think that we can do better than that in these built conditions, and we're starting to document that now. Of course, where it gets interesting is when you look beyond just a single benefit and you start to think about what can we do to bundle green infrastructure together to get a broader scale of benefit. Well, here's a couple of examples of communities in Iowa that have started to do that. And we're just looking at lighting retrofits. So Algona, Iowa, retrofitted 447 fixtures with LED lighting systems, estimated an overall about 42% energy cost reduction. $288,000 to install, annual cost savings of almost $19,000, estimated life cycle savings over $500,000, 15-year estimated return on investment. Auburn, Iowa, they just retrofitted 24 fixtures, 78% energy reduction, about $12,500 total cost, about $5,000 or $4,500 annual cost savings, $82,000 estimated cost on the cycle, 2.8 year estimated return on investment. Now the interesting thing, like most of these green infrastructure opportunities, is that you have eligibility for grants. So both of these communities got a 50% cost share. So now their return on investment is 7.5 years, and your return on investment is just over a year. That's just energy. Now you start to bundle that in with green streets. How about district energy systems? Well, I'm going to talk about that in a second. This is Iowa's Green Street Pilot Project, which we designed in West Union, Iowa, little town, rural county community, 2,500 population, Fayette County up in northeastern Iowa. In 2007, the Iowa Economic Development Authority decided to institute a Green Streets program within their Main Streets program in the state, thinking that that would kind of maybe enlist a little bit of reinvestment in our Main Street communities throughout the state. So we got involved, and we went to the IEDA, did a little presentation about it, because they were thinking, okay, maybe we just put in some energy efficient lights and things like that. They didn't really think about what it could be beyond that. So we came in. Here's West Union, has little trout streams that run along the edge of town, get out into this Otter Creek ways out of town. Unfortunately, as when we started, the water was too hot and polluted near town to support any kind of fish life of any particular benefit. So one of the things that we started to do was the Department of Natural Resources came in with us and started doing baseline studies so that we could document the Green Street changes in terms of water quality, water temperature, and could that by itself help invigorate the fish population moving right back up into downtown so the kids could ride their bicycle a couple of blocks from Main Street and go fishing right in the middle of town. So we're actually studying that. So what we did here, big cross section street, 100 foot wide from building facade to building facade cross section. In a slightly hilly town, you're right at the cusp between the driftless area and glaciated regions of northeastern Iowa. So you got a little bit of hill in here and an aging population. You imagine trying to walk across the street with a stroller thing and see a pickup truck come flying over the hill about 45 miles an hour. Well, that was what was going on here, fairly routinely. So what we did, the IEDA had already started an architectural facade restoration program, which most of the Main Street communities throughout, and all Main Street programs throughout the country have a pretty strong architectural historical facade restoration program. And we essentially came in and designed the retrofit from building facade to building facade of the entire cross-section of the street. And that includes porous, interlocking porous paved streets, integrated bioretention. We want water to be visible. Why put it in a pipe? Putting it in a pipe and sending it to someplace else doesn't do anybody any benefit. If we can actually see how the water is moving through the system and make water part of the hard element, then it becomes a point of reconnection. Porous sidewalks. Everything's porous. The entire cross-section is porous. So when it rains, the water's going in, we migrate it towards the middle. We're getting infiltration based upon the different characteristics of the soil, and you just design that right in. Actually, we have pretty good soils in Charles City. Here, just really clay. We have really clay soils most of the place, but that isn't the problem. As long as we design that into the system with your bioretention. Now, we started to bundle more here. We have district-wide geothermal heating and cooling. That by itself, prior to the natural gas prices plunging a bit, was estimated to save over $100 million in energy cost savings to the community, just the 6 blocks of downtown in the next 50 years. That would have paid for the entire project 10 times over. So, okay, so that's just the energy system. But we also have LED, very high energy efficient lighting. We have electric car plugs. We have, recyclable materials. This isn't just designed as a green street from the perspective of water and energy. It's designed as a complete green street, is what I refer to it, because now pedestrian and bicycle safety, traffic calming, everything has been designed in here with an intent to bring back the elements of the historical architecture, the materials of that community. Very unique. So this is what the county's courthouse square looked like originally, with water running down the surface. And this is what it looks like now. It has an amphitheater. We harvested the original brick and brought that right back up and incorporated it into the cross-section of each one of the main intersections. And then we've designed very safe places, mid-block bump outs, and this is during construction, so it hadn't even been vegetated yet. The formal ribbon cutting on this was in July. Essentially build it and they come. And I'll talk a little bit more about that in a minute. The IEDA is in the process still of doing an economic impact study of what's happened to this community as a result of this project. And that isn't out yet, but I have another one for you. And so, again, during construction, hadn't even been planted yet. Now you have infrastructure that handles it. There'd never be another state or federal dollar that was ever allowed to be spent on single-purpose infrastructure. A street should be your water management system. It should solve your problem, not for you, not send it someplace else. It should be part of your energy system. And then before and afters. So you have beautiful infrastructure that'll last the better part of a lifetime, that pays for itself over and over. In fact, I'll talk about that in just a second. So they said, and then, actually celebrates their own cultural and history, their natural history of the community. Now, when we were looking at from the very early concepts through schematic design development, construction documents, we had to continually assess what the costs and benefits were going to be for a system like this versus the costs and benefits for conventional infrastructure. We wanted to make sure, there was a lot of communications and outreach, as you might anticipate, and funding support. Well, the interesting thing about this is, again, what we had: permeable pavers, green gardens, energy-efficient lighting, district geothermal, accessibility, complete streets, amphitheaters, plug-in stations, new water lines, new sanitary lines, et cetera, et cetera. But when we were looking at just the cost of the street versus this green street versus a conventional street with a storm sewer system, we had to look at that just by itself. And based on if you had a conventional street and you had this kind of a street system, what were the cost comparisons going to be with conventional maintenance. Now you've got to understand, you don't have any more patching, you don't have any more milling and resurfacing. You don't have to do that anymore. You're not going to have the same kind of winter maintenance. The systems are very well aerated, so when it warms up, the water melts. It goes into your system down below, into your storage, and you don't have water wicking back up. The system is flexible, it can breathe without fracturing, so you're not out there patching potholes. You're using less salt. Your maintenance is going to be reduced. And so, again, using the most conservative estimates, we looked at that, just that piece of it. And it was a 15-year return on investment before just was street, conventional street and storm sewer versus our street and storm sewer. Of course, this also included sanitary, excuse me. So 15 years out, just from there, they had this beautiful, complete green streets paid for. But when you start to look at bundling the other benefits, that's really where it starts getting interesting. Now, the other thing that's interesting is when you don't have single-purpose infrastructure, but rather you have multi-beneficial infrastructure, that's where the street is not just a street, part of the energy. Now, all of a sudden, because of multiple benefits, you are eligible for grant funding entities that you would not be eligible with normal infrastructure. So we got money from the Department of Transportation, we got DNR, Department of Agriculture, US EPA, Department of Energy, IJobs. I mean, it just kept going on and on and on. Now, originally, they were looking, and one of the reasons that this was selected as the candidate for being the pilot project is they were just getting ready to start a complete retrofit of their infrastructure. New sidewalks, new sanitary, new storm, new water lines, new streets. And they were anticipating that build out would have been about $4.5 to $5 million, of which they would have gotten some element of federal public support, and then they were going to have to bond for at least $3 to $3.5 million of that $4.5 to $5 million. What we ended up doing is getting about a project that's about $9.5 million with $7.5 million to $8 million of grants. And they, as a aging community, ended up having to pay less in terms of their own bonding than they would have. Yet, and that's just looking at direct payback. So, when you start to really put all the pieces together, you move outside of the streets. Now you've got your streets, you've got your district energy systems, you've bundled energy and water and begun to look at waste. And then you go outside of that cross section. What else can you do? Well, you can do, because rainfall falls everywhere, you can do these solutions everywhere. So let's take your local police station. This is Villa Park's police station, a LEED certified new police station built in 2003, or 2005, excuse me. Integrated extensive green roof systems. All the pavement systems are modular porous pavement systems. Integrated bioretention. You're not using 10 to 15% of the site for a hole in the ground. In fact, that's one of the benefits. When you design integrated green infrastructure, you eliminate conventional detention systems. You don't need them anymore. So you design the system to essentially all function together so that when the water goes into your drainage layer, it slowly moves out under your parking areas into the bioretention. And of course, we have the overflow mechanisms built into this, just like you would with any conventional kind of storm sewer approach. The issue here is that since this was finished construction in 2005, and we've had several 100-year plus rainfall events since then, there's never been any runoff. On a 3/4 acre infill, never any runoff. We've never breached our overflow standpipe. It's not that difficult to do if that's how you approach it from the beginning of the project. The new Ann Arbor Municipal Center expansion, water as art, water integrated into the site in very, very beautiful ways. When it rains, fun stuff happens. It's not that difficult if you think about that. Educational facilities, wonderful opportunities for education. Yeah, doing okay. That was the E.P. Tyner Interpretive Nature Center LEED Platinum project in Glenview, Illinois. Parsons Park, the little park at Parks in the city of Chicago. All these little interpretive elements. When it rains, the water moves through the system and migrates into little bioretention areas. We've worked with other communities on their park and open space systems, so you integrate the play and the water and all the environmental impacts together. In the Quad Cities, we have the Retain the Rain program. Just wonderful opportunities to outreach. Queens Botanic Garden, their LEED Platinum new headquarters complex. We did the master plan for the 38-acre Botanic Garden, and then worked with the architects and building systems engineers. This was the first LEED Platinum certified public building in New York City when it was actually had the ribbon cutting back in 2008. And again, water. Everything that you see here, they handle their own rainwater and wastewater, and then we harvest water, use that for the non-potable gray water in the buildings, but water as art. So everything, all of the art elements are all driven around water, but it's all collected rainwater. We use no potable water for any of these systems. And water is art. So the art is actually part of our functional, complete, holistic site water management system. And I know you're doing things like that here. We were down at the TransPro site last night. You know, you've got some really cool things going on. So it's just a matter of kind of applying our focus in that. Kresge Foundation Headquarters Complex, Troy, Michigan, basic, complete on-site rainwater harvesting and reuse and absorption. Forest pavement, rainwater harvesting, integrated water features, native landscapes. Education is a big part of this. They do a lot of granting. If you've ever worked with Kresge Foundation, everything has to be green. Speaking of education, I can't imagine a better way to reconnect us as people today with an understanding of these whole system sort of approaches and how the world works around us than to implement these concepts right into our schools, whether it's K through 12, our colleges and universities, create whole new opportunities for research, for student and faculty education and outreach at the community level, hospitals, healthcare. I mean, we're all about health here. And this is actually the 11-story bed tower at Advocate Lutheran General in Park Ridge, Illinois. Extensive green roof systems up on top of the 11th story.